something vast and invisible holds the universe together, and we have never once touched it. Welcome to the Sleepy Lab. Tonight, we drift through one of the quietest mysteries in all of science, dark matter. What it might be, how we know it's there, and why, after decades of searching, it remains just beyond our reach. If you'd like to drift through more nights like this one, a quiet subscription means a great deal, one sleepy soul at a time. Now, let's begin. Take everything you have ever seen, every mountain, every ocean, every star scattered across a clear night sky, every galaxy photographed by every telescope ever built. All of it, every atom of it, adds up to about 5% of what the universe actually contains. 5%. The rest is something else entirely. Roughly 27% of the universe is made of what scientists call dark matter. Not dark in the way a room is dark when the lights go out. Dark in a deeper sense, invisible to every instrument we have ever made. Silent across every wavelength of light. It does not glow. It does not reflect. It does not absorb. And yet it outweighs everything we can see by nearly 6 to 1. The remaining 68% is something else again, dark energy. A separate mystery, a kind of pressure woven into space itself, pushing the universe apart. Dark energy and dark matter share a name, but they are entirely different puzzles. Tonight, we rest with only one of them. The first person to sense that something was missing was a Swiss astronomer named Fritz Zwicky. The year was 1933. Zwicky was studying a vast collection of galaxies called the Coma Cluster, hundreds of galaxies bound together by gravity, drifting through space as a single enormous family. He measured how fast those galaxies were moving within the cluster, and what he found did not make sense. They were moving far too fast. In any gravitational system, there is a kind of balance. The mass of the system pulls inward, and the motion of its members pushes outward. Too much motion, and the whole thing flies apart. The galaxies in the Coma Cluster were moving with enough speed that, by all rights, the cluster should have dissolved long ago. The visible mass, all those hundreds of galaxies, simply was not enough to hold them. Zwicky proposed that there must be additional mass that could not be seen. He called it dunkel materie, dark matter. For a long time, the idea was noted and quietly set aside. It would take another 4 decades before the evidence became impossible to ignore. In the 1970s, an astronomer named Vera Rubin, working alongside her colleague Kent Ford, turned her attention to spiral galaxies. Galaxies like our own Milky Way, with long, graceful arms curling outward from a bright central core. She wanted to measure how stars within those galaxies moved. Specifically, how fast they orbited around the galactic center. There is a pattern that gravity predicts. Think of our own solar system. Mercury, closest to the Sun, races around its orbit in just 88 days. Neptune, far out in the cold dark, takes 165 years to complete a single loop. The farther from the center of mass, the slower the orbit. This is simply how gravity works. It has been understood since Newton. Rubin expected to see the same pattern in galaxies. Stars near the bright central bulge should orbit quickly. Stars far out in the dim outer reaches should orbit slowly. That is not what she found. The stars far from the center were moving just as fast as the stars near the middle. The rotation curve, a graph of orbital speed against distance from the center, was flat, not falling away as gravity predicted. Just flat, all the way out to the edge of the visible disk and beyond. This was not a small discrepancy. It was not a measurement error. Rubin checked galaxy after galaxy, and the pattern held. Dozens of spiral galaxies, all showing the same quiet impossibility. For the rotation curves to be flat, there had to be more mass, not concentrated in the bright center, but spread out, distributed in a vast, invisible halo surrounding the entire visible galaxy. A halo of something that contributed gravity without contributing light. The stars we see are, in a sense, just the surface. Beneath them, around them, extending far beyond the last visible star, there is something else, something enormous and silent, shaping every orbit, holding every galaxy together. Zwicky had glimpsed it in the motion of a cluster. Rubin had traced it in the spin of individual galaxies. And slowly, carefully, the scientific community began to accept what the numbers were saying. Not because anyone wanted to believe in invisible matter. Scientists are, by nature, reluctant to add things to the universe that cannot be seen. But the evidence was patient. It accumulated quietly, from multiple directions, each line of reasoning pointing to the same conclusion. Something is there. We simply cannot see it. There is a quality to this mystery that is worth sitting with for a moment. We tend to think of the unknown as something distant, something at the edge of the universe, or at the beginning of time. But dark matter is not distant. It is here, in this room, passing through the walls, passing through you, right now, in this very moment. If the leading candidates are correct, roughly 100,000 dark matter particles may be passing through a space the size of your hand every single second. And you feel nothing. Not because the particles are small, exactly, but because they do not interact with the matter that makes up your hand, or the air around it, or the instruments we have built to detect such things. They pass through as if the ordinary world simply does not exist for them. We are, in a sense, ghosts to each other. What Zwicky noticed in 1933, and what Rubin confirmed across decades of careful observation, was not a flaw in our measurements. It was a window into a universe far larger and stranger than the one we thought we lived in. 5%. That is our share. The stars, the planets, the oceans, the atoms in every living thing, all of it, just 5% of what is actually here. The rest moves quietly around us, through us, holding everything in place. And we are only just beginning to learn how to listen for it. There is a simple rule that governs how things orbit. When you move further from the center of a gravitational system, you move more slowly. This is not a theory. It is something we can watch in our own solar system, patient and reliable as the seasons. Mercury races around the sun in 88 days. Mars takes nearly 2 years. Saturn, far out in the cold, takes almost 30. The farther you go, the weaker the sun's grip and the more gently you are carried along. This pattern holds because most of the mass in our solar system sits at the center, the sun. Everything else is a rounding error by comparison. So the planets farther out feel less pull, and they slow accordingly. Astronomers expected galaxies to behave the same way. A spiral galaxy has a bright central bulge, dense with stars. Moving outward, the disk thins. The stars become more scattered. The light fades. And so, by the same logic that governs our solar system, the stars and gas clouds at the outer edges of a galaxy should orbit more slowly than those near the center. The math was clear. The expectation was reasonable. It was wrong. When Vera Rubin and Kent Ford turned their instruments towards spiral galaxies in the 1970s, measuring the velocities of gas clouds at different distances from each galactic center, they found something that did not fit. The rotation curves, the graphs plotting orbital speed against distance, did not fall. They stayed flat. Stars and gas far out at the edges of galaxies were moving just as fast as those much closer in, sometimes faster than they had any right to. This was not a small discrepancy. It was not the kind of thing you could explain away with measurement error or a slightly different assumption. The outer regions of galaxies were moving so fast that, if only the visible matter were holding them, they should have flown apart long ago. The galaxies should not exist in the shapes we see them. And yet, there they were. The only explanation that made the numbers work was mass, invisible mass, not concentrated at the center, but spread out, distributed in a vast, diffuse halo surrounding the entire visible disk. A halo so large and so heavy that its gravitational reach extended far beyond the last visible star, holding the outer edges of the galaxy in their orbits as firmly as the inner ones. The Milky Way's own halo, as best we can estimate, extends roughly 100 times farther than the visible stellar disk, the disk of stars and gas you might picture when you think of our galaxy. That bright, flat spiral is, in a sense, just the small, bright center of something far larger and far darker. A structure we cannot see, but whose gravitational presence is written into the motion of everything we can. This was one window into the hidden universe. There is another. Light does not travel in straight lines through a universe filled with mass. Mass curves space-time. This was one of Einstein's great insights. And when space-time curves, the path of light curves with it. A beam of light passing near a massive object will bend, deflected by the geometry of the space it moves through. The more mass, the more bending. This effect is called gravitational lensing, and it turns massive objects into natural telescopes. A galaxy cluster sitting between us and something more distant will distort the light from that distant object, stretching it, bending it, sometimes splitting it into multiple images arranged in arcs around the foreground mass. In the most precise alignments, when a background galaxy, a massive foreground object, and Earth fall almost perfectly along a single line of sight, the background galaxy's light is bent into a complete ring, a circle of light surrounding the foreground mass, thin and luminous and strange. These are called Einstein rings, and they are among the more quietly beautiful things the universe produces. But gravitational lensing is more than beautiful. It is a measurement. The degree to which light bends around an object depends on how much mass that object contains. By carefully measuring the distortions, the arcs, the rings, the subtle stretching of background galaxy shapes, astronomers can calculate how much mass must be present to produce that bending. And when they do this for galaxy clusters, the answer is always larger than what the visible matter can account for. Always. The stars, the gas, the dust, everything that glows or absorbs or reflects adds up to far less than the lensing requires. The light is being bent by something that does not shine, something that is simply there, massive and invisible, curving space-time just as faithfully as any star. This is not a subtle effect. In some clusters, the lensing implies several times more mass than all the visible matter combined. The discrepancy is not at the edge of measurement uncertainty. It is large, and it is consistent, and it appears wherever astronomers look. There is a particular kind of lensing that works across much larger scales, and it is perhaps the most patient of all the methods we use. Weak gravitational lensing does not produce dramatic rings or bright arcs. Instead, it leaves a faint statistical imprint on the shapes of millions of background galaxies. A galaxy that would otherwise appear round is stretched very slightly by the mass between it and us. One galaxy tells you almost nothing. Galaxies come in all shapes. But a million galaxies, all stretched in subtly correlated directions, carry a signal, a map. By analyzing these patterns across wide regions of sky, astronomers can reconstruct where mass is concentrated, not just where light is concentrated. The maps that emerge show a universe where mass and light do not always coincide, where the heaviest regions are sometimes the darkest. And this brings us to one of the clearest demonstrations we have. Two galaxy clusters, each containing hundreds of galaxies and vast clouds of hot gas, collided and passed through each other. The collision happened long ago, and what we observe now is the aftermath. Two clusters that have moved apart, each carrying the evidence of what happened when they met. The hot gas, which makes up most of the ordinary matter in a galaxy cluster, was slowed by pressure as the two clouds of gas collided and interacted. It lagged behind. X-ray telescopes can see this gas clearly. It glows at temperatures of tens of millions of degrees, and it sits between the two clusters, displaced from where the galaxies themselves ended up. But the gravitational lensing maps tell a different story. The mass, the bulk of the mass, did not slow down. It continued forward with the galaxies, passing through the collision as if the other cluster were not there at all. The two mass concentrations moved through each other, separated cleanly, and came out the other side. This is the bullet cluster, and it is one of the most direct pieces of evidence we have that dark matter is real and that it behaves differently from ordinary matter. The gas interacted. The dark matter did not. The mass and the light came apart, visibly, measurably, in a way that is very difficult to explain without invoking something that does not interact through pressure or electromagnetism. Only gravity. Three independent lines of evidence: the motions of stars and galaxies, the bending of light around clusters, and the separation of mass from gas in a collision, all point toward the same conclusion. There is more here than we can see, far more. And it is not hiding in some exotic corner of the universe. It is everywhere, in the halo surrounding our own galaxy, in the space between the stars, passing through this room, through the walls, through you, in this quiet moment. The universe is mostly something we have never touched. And yet, the bullet cluster is only one place in the sky. Astronomers have found ways to trace dark matter not just in dramatic collisions, but quietly across vast stretches of the cosmos, using nothing more than the subtle warping of light. When light from a distant galaxy travels toward us, it passes through the gravitational fields of everything between that galaxy and our eyes. Every concentration of mass along the way bends that light very slightly, not enough to form a ring, not enough to produce a dramatic arc, just enough to stretch the image of the background galaxy by a fraction of a percent to make it appear very slightly more elongated than it truly is. This is called weak gravitational lensing. A single distorted galaxy tells you almost nothing. The distortion could simply be the galaxy's own shape. But when you look at thousands of galaxies behind a region of sky, and you find that their shapes are all stretched in the same direction by similar amounts, that is not coincidence. That is the signature of mass between you and them. Mass that is bending space in a coherent, measurable way. By carefully measuring these tiny alignments across millions of background galaxies, astronomers can reconstruct where the mass is, not just where the light is, not just where the gas is, but where the gravitational influence is concentrated. And what they find, again and again, is that the mass does not follow the light. The maps that emerge from weak lensing surveys show enormous structures, filaments of invisible material stretching between galaxy clusters, halos of dark matter surrounding individual galaxies, vast underdense regions where very little of anything seems to gather. These maps match, with quiet precision, the maps predicted by simulations that include dark matter. They do not match simulations that leave it out. So we have the rotation of stars, the bending of light, the separation of mass from gas in a collision, and now the large-scale architecture of the cosmos itself, traced through the distortion of 100 million distant galaxies, all of it pointing in the same direction. There is something here that we cannot see. And the question that follows naturally, the one that has occupied physicists for decades now, is not whether dark matter exists. The evidence for its gravitational presence is too consistent, too independent, too difficult to dismiss. The question is what it actually is. What kind of thing interacts with gravity, but with almost nothing else? As far as we can tell, dark matter does not interact electromagnetically at all. It does not emit light. It does not absorb light. It does not reflect it. There is no wavelength, no frequency, no color of radiation that dark matter produces or responds to. Infrared, ultraviolet, radio waves, X-rays, gamma rays, none of them touch it. None of them are touched by it. This is why it is invisible not just to our eyes, but to every telescope ever built. Every instrument we have for observing the universe is, in some way, an instrument for detecting electromagnetic radiation, and dark matter simply does not participate in that conversation. It may interact through the weak nuclear force, the same force responsible for certain kinds of radioactive decay. If it does, those interactions would be extraordinarily rare. A dark matter particle passing through the entire Earth would almost certainly pass through without a single collision. The Earth, to dark matter, is mostly empty space. And yet, gravity it does have. Gravity it exerts, and gravity it responds to. That much is certain. That much is written into the structure of everything we observe. The computer simulations make this especially clear. When cosmologists model the formation of the universe, starting from the nearly smooth state of the early cosmos and running the physics forward through billions of years, they find that the structures they produce depend critically on what they put in. A simulation with only ordinary matter, only the protons and electrons and atoms we know, does not produce a universe that looks like ours. The galaxies that form are distributed differently. The clusters are wrong. The great filaments and voids of the cosmic web do not emerge in the right proportions. The universe in the simulation looks like a place where something is missing. When dark matter is added, when the simulation includes a component of matter that interacts only gravitationally, that began clustering earlier than ordinary matter could, that formed the invisible scaffolding into which gas and stars later fell, the universe that emerges looks right. The filaments appear. The clusters form at the right scales. The distribution of galaxies across the sky matches what we actually observe. This is not a small adjustment. It is not a minor correction to an otherwise working model. Without dark matter, the simulations fail. With it, they succeed. And they succeed not because dark matter was tuned to fit the observations after the fact, but because the same dark matter density inferred from galaxy rotation curves, from gravitational lensing, from the cosmic microwave background, that same density, plugged into the simulations, produces a universe that looks like home. The consistency across such different methods, across such different scales, across observations made by different teams using different instruments over many decades, that consistency is what makes the case so difficult to set aside. And yet, no one has ever directly detected a dark matter particle. Not once. Not in any laboratory, in any experiment, in any detector. We know it is here. We know it is passing through this room right now. Through the walls, through the air, through the quiet weight of your body resting in the dark. We know it because of what it does to everything around it. But we have never caught it, never made it stop, never made it leave a mark we could point to and say, there, that was dark matter. That was the thing itself. This is the strange position physics finds itself in. Certain of the presence, uncertain of the nature, confident in the shadow, unable to find the object casting it. Dark matter does not cool. It does not radiate energy away the way ordinary matter does. When a cloud of gas collapses under gravity, it heats up, and then it radiates that heat away as light. And then it can collapse further, and eventually it forms a star, or a disk, or a dense compact structure. Dark matter cannot do this. It has no way to shed energy, so it does not collapse into disks. It does not form stars. It settles into large, diffuse, roughly spherical halos, slowly deepening their gravitational wells over billions of years, but never condensing, never brightening, never announcing itself. This is part of why it has been so difficult to find. It is not hiding in some dense, detectable clump. It is spread across enormous volumes of space, thinly, evenly, quietly. The halo surrounding our own galaxy extends perhaps 100 times farther than the visible disk of stars. It contains, by some estimates, roughly 1 trillion times the mass of the sun. All of it invisible, all of it inferred, all of it real. In the only sense that matters, it is there. It has weight, and without it, the Milky Way, as we know it, would not hold together. You are inside that halo right now. You have always been inside it. Every moment of your life has taken place within this vast, invisible structure that you have never seen and never felt and never had any reason to think about. And yet it has been there, surrounding everything, shaping everything, since long before the first star ever formed. The visible universe, the stars, the planets, the light, is something like the surface of a much deeper thing. A quiet architecture, holding it all in place. And so we find ourselves here, inside something we cannot see, resting within a structure that has no surface, no edge we could ever reach out and touch. It is worth staying with that for a moment. Not with urgency, just with quiet attention. Because what comes next is perhaps the most remarkable part of the story. The evidence for dark matter does not come from one place. It does not rest on a single observation, a single measurement, a single scientist's intuition. It comes from many directions at once. From the rotation of galaxies, from the bending of light, from the way clusters of galaxies move, and from something else entirely. From the large-scale shape of the universe itself. When astronomers look out across hundreds of millions of light years, they see a pattern. Galaxies are not scattered randomly through space. They gather into long, thin filaments, vast threads of light and matter stretching across the cosmos. And between those threads, there are voids, enormous regions of near emptiness, some of them hundreds of millions of light years across. This structure, the cosmic web, as it is sometimes called, is one of the largest things we know of, and it can be modeled. Astronomers run simulations of the universe on large computers. They begin with the conditions of the early cosmos and let gravity, pressure, and time do their work. When those simulations include dark matter, the result matches what we observe. The filaments form. The voids open up. The clusters gather at the intersections of threads, just as they do in the real sky. When dark matter is removed from those simulations, the web does not form. Not quite. The structure comes out wrong. Too smooth in some places, too clumped in others. The galaxies do not arrange themselves the way they actually do. Something is missing, and that something, in every simulation that has been carefully constructed, turns out to be the invisible mass. This is not a small discrepancy. It is not a matter of fine-tuning. Without dark matter, The large-scale structure of the universe simply does not emerge in the way we observe it. And there is another line of evidence, one that reaches even further back. Long before any galaxy existed, before any star had formed, the universe was filled with a hot, dense plasma. Light and matter were coupled together, moving as one. And through that plasma, sound waves traveled, slow, deep pressure waves rolling through the primordial fog. For about 380,000 years, those waves moved. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen. And in that moment, light was released. It streamed freely across space for the first time, carrying with it a faint imprint of everything that had happened before. That light is still traveling. It reaches us today as the cosmic microwave background, a faint glow of ancient radiation filling the entire sky, cooled now to just a few degrees above absolute zero, but still carrying, encoded in its subtle temperature variations, the memory of those early sound waves. The pattern of those variations, the precise ratios of their peaks and troughs, is extraordinarily sensitive to the composition of the early universe, to how much ordinary matter was present, and how much dark matter. Ordinary matter and dark matter respond differently to those pressure waves. Ordinary matter is pushed and pulled by radiation. Dark matter is not. It does not interact with light. It does not feel that pressure. And so the two components leave different fingerprints in the pattern. By measuring those fingerprints carefully, astronomers can read off the density of dark matter with remarkable precision. The Planck satellite, which mapped the cosmic microwave background in fine detail, gives a dark matter density of roughly 0.26 times what is called the critical density of the universe. That number, arrived at from the oldest light in existence, agrees with the number derived from galaxy rotation curves, from gravitational lensing, from the behavior of galaxy clusters. Different methods, different observations, different centuries of science, all pointing to the same answer. And the reason dark matter leaves such a clear imprint on the early universe comes down to timing. In those first hundreds of thousands of years, ordinary matter was locked in step with radiation. The pressure of light prevented it from collapsing under its own gravity. Every time ordinary matter tried to fall inward, radiation pushed it back out. It could not yet begin to form structure. Dark matter had no such constraint. Because it does not interact with light, it felt no radiation pressure. It was free to begin clustering gravitationally from very early on, while ordinary matter was still being held in place by the pressure of the primordial light. Dark matter was already quietly gathering, slowly deepening the gravitational wells of the universe. By the time ordinary matter was finally released, when the light streamed free and the pressure lifted, dark matter had already done much of the work. The wells were already there. Ordinary matter fell into them. Those concentrations of dark matter, the overdense regions that had been quietly accumulating for hundreds of thousands of years, became the seeds of everything that followed. Ordinary matter flowed down into those gravitational hollows, gathered, cooled, condensed, and eventually, over hundreds of millions of years, formed the first stars, the first galaxies, the first light in a universe that had until then been entirely dark. In a very real sense, dark matter did not just accompany the formation of galaxies. It preceded it. It prepared the ground. Every galaxy we have ever observed, every spiral, every elliptical, every irregular smear of stars across the sky, formed inside a dark matter halo that was already waiting. And some of those galaxies carry the evidence of this more plainly than others. There are small galaxies, dwarf spheroidal galaxies. They are called that orbit larger ones like our own Milky Way. They're faint. Some contain only a few million stars. They are among the smallest gravitationally bound stellar systems we know of. And yet, they are some of the most dark matter-dominated objects in the universe. In some of these dwarf galaxies, the ratio of dark matter to visible matter is extraordinary, hundreds to one. In some cases, for every unit of mass that shines, there may be hundreds of units of mass that do not. The stars are almost incidental, a faint trace of ordinary matter sitting at the center of a dark matter structure far larger and more massive than anything visible. They are, in a sense, the purest examples of what dark matter does. Stripped of most of their gas and dust by gravitational interactions with larger galaxies, left with only their stars and their halos. These small systems show us the underlying architecture with unusual clarity. The dark matter is not a supplement to the visible matter in these galaxies. The visible matter is almost a footnote to the dark matter. A few million stars, quietly burning, held in place by something hundreds of times more massive that emits no light at all. And this is the picture that has emerged, slowly, over decades of observation and measurement and careful thought. A universe in which the visible, the stars, the gas, the dust, the light, is a kind of surface. Beneath it, around it, preceding it in time, is the dark, not threatening, not cold in any felt sense, simply present, simply there, the quiet majority of everything that has mass in the cosmos, shaping the universe from the very beginning, still shaping it now. Some of those dwarf galaxies contain hundreds of times more dark matter mass than stellar mass. Not a little more, not twice as much, hundreds of times. A galaxy that might hold a few million stars, each one a sun, each one burning, surrounded and suffused by something so much more massive that the stars themselves are almost incidental. It is a strange thing to sit with. The light you would see, looking at such a galaxy through a telescope, represents only a small fraction of what is actually there. The rest is invisible, present only in the way it bends the paths of things, holds things in place, keeps the stars from drifting away into the wider dark. And so the question that has occupied physicists for decades is a quiet but urgent one. What is it? Not where is it. We have a reasonable sense of where it is, not how much of it there is. The measurements are consistent and careful. But what, exactly, is the thing itself? The most widely studied candidate has a name that is almost too convenient: the WIMP, a weakly interacting massive particle. The name was coined partly because of what such a particle would do, and partly, perhaps, because physicists have a quiet sense of humor about these things. But the physics behind it is serious, and the reasoning is careful. A WIMP would be a particle with mass, real, substantial mass, somewhere between roughly 10 and 1,000 times the mass of a proton. That is not a small thing. A proton is already a compact, dense object. A particle 1,000 times heavier would be genuinely massive by the standards of the subatomic world. And yet, it would pass through ordinary matter almost without noticing it. This is what weakly interacting means. It would not respond to electromagnetism. It would not absorb light or emit it. It would interact, if at all, only through gravity and through the weak nuclear force, the same force responsible for certain kinds of radioactive decay. The weak force is, as its name suggests, weak interactions mediated by it are rare. A neutrino, which also interacts only weakly, can pass through a light year of solid lead with only a modest chance of being stopped. a WIMP would be similarly elusive, perhaps more so. And yet, in principle, it could be detected. Because the weak force, rare as it is, does occasionally cause things to happen, given enough material and enough patience and enough shielding from everything else that might mimic a signal, a WIMP passing through a detector might, very rarely, collide with an atomic nucleus, leaving behind a faint trace of energy, a small recoil, a whisper in the data. Detectable in principle, extraordinarily rare in practice. This tension between theoretical accessibility and practical elusiveness has defined dark matter research for a long time now. But there is a reason WIMPs became the leading candidate, and it is not simply that they seem detectable. It is something more elegant than that. Physicists call it the WIMP miracle. It is not a miracle in any mystical sense. It is a coincidence, a numerical one, that is striking enough to feel like a clue. When you take a particle with roughly weak-scale mass and weak-scale interactions, and you calculate how many of them would have been produced in the hot early universe, and how many would have survived as the universe cooled and expanded, the number you get is very close to the observed dark matter density. You did not design the particle to produce that number. You did not tune the parameters to fit the observation. You simply took the physics that was already being developed for other reasons. The physics of the weak force, the physics of particles at that mass scale, and the answer came out right. That kind of coincidence tends to attract attention. It does not prove that WIMPs are real. A coincidence is not a confirmation. But it suggests that if nature chose to make dark matter out of particles at that mass and interaction scale, the accounting would work out. The universe would contain roughly the right amount. And so the search began, and has continued, for decades now. But WIMPs are not the only candidate. There is another, quite different possibility, one that emerged not from cosmology at all, but from a problem deep inside the theory of the strong nuclear force. In 1977, a physicist named Roberto Pecci and a physicist named Helen Quinn proposed a solution to a puzzle in quantum chromodynamics, the theory that describes how quarks and gluons behave inside protons and neutrons. The puzzle had to do with a symmetry that the theory seemed to allow, but that nature did not appear to use. A symmetry that, if broken in a certain way, would cause the neutron to have a measurable electric dipole moment, and yet measurements showed the neutron's dipole moment to be extraordinarily small. Perhaps zero. This is known as the strong CP problem, and it is a genuine puzzle. Why would nature allow a symmetry violation and then choose, apparently, not to use it? Pecci and Quinn proposed a mechanism that would dynamically suppress this violation, and as a consequence of their mechanism, a new particle would exist. Frank Wilczek and Steven Weinberg, working independently, identified this particle and gave it a name, the axion. The axion was not proposed to explain dark matter. It was proposed to explain something else entirely. But when physicists examined its properties, they found something interesting. An axion would be extraordinarily light, perhaps a billionth of a billionth the mass of an electron, so light that it barely registers on any scale we normally use for particles, and it would interact with ordinary matter almost not at all. Almost. In the presence of a strong magnetic field, an axion could, in principle, convert into a photon, a real, detectable particle of light. The conversion would be rare, the signal would be faint, but it would be there. And crucially, if axions exist in the right abundance, and if they were produced in the right way in the early universe, they could account for the dark matter density we observe. A particle proposed to solve one problem, quietly solving another. There is something almost restful about that kind of convergence. Two separate threads of physics, pulled from different directions, meeting at the same quiet point. The axion is a different kind of candidate from the WIMP, lighter by an almost incomprehensible margin, interacting differently, requiring different experiments to find. Where WIMP searches look for nuclear recoils in heavy, cold detectors deep underground, axion searches look for faint photon signals inside carefully tuned microwave cavities, bathed in powerful magnetic fields. Different instruments, different signatures, different corners of the same vast unknown. And this is part of what makes the search for dark matter so patient, so methodical, so quietly ongoing. There is no single experiment that could rule out all candidates at once, no single observation that would close the question. Each candidate requires its own approach, its own technology, its own years of careful data collection and analysis. The universe has not yet told us which path leads to the answer. It has only told us, with considerable consistency and from many different directions, that something is there. Something with mass, something that shaped the cosmos from its earliest moments, something that surrounds every galaxy, including our own, passing through this room, through you, through everything, in numbers that are difficult to hold in the mind. Quietly, without leaving a mark we have yet learned to read. The axion, if it exists, is almost nothing. Not in the dismissive sense, but in the most literal, physical sense. It would carry a mass so small that our usual units of measurement feel almost embarrassed to describe it. A billionth of a billionth the mass of an electron. And an electron is already among the lightest things we know. To hold that number in the mind is to feel the mind quietly let go of it. It is not a number that resolves into an image. It simply recedes. And yet, mass, however small, is still mass. And a particle with mass, however ghostly, is still a particle, still something rather than nothing, still a candidate for the invisible architecture that holds the cosmos together. The axion was not invented to explain dark matter. That is one of the quieter ironies of this search. It was proposed in 1977 to resolve a separate tension entirely, a problem deep inside quantum chromodynamics, the theory that describes how quarks bind together inside protons and neutrons. The mathematics of that theory seem to permit a certain kind of symmetry violation that has never actually been observed, and the axion was introduced as a way to explain why that violation does not occur, a solution to one puzzle that may, quietly, also solve another. Because if axions exist in sufficient numbers, if they were produced in the right quantities in the early universe, they could account for the dark matter density we observe today. Two problems, one particle, though of course that remains to be confirmed. What makes the axion so difficult to find is precisely what makes it a plausible dark matter candidate. It interacts almost not at all. It passes through ordinary matter, as though ordinary matter were not there, which, from the axion's perspective, it very nearly is not. Under normal circumstances, an axion would leave no trace, no recoil, no heat, no signal of any kind. But there is one exception. In the presence of a strong magnetic field, an axion can, under certain conditions, convert into a photon, a real, detectable photon. The process is subtle and the conversion rate is low, but it is not zero. And in physics, not zero is everything. This is the principle behind a class of experiments that look nothing like the heavy xenon tanks buried deep underground. Instead of tons of cold liquid shielded from the world, these experiments use something more like a tuned instrument, a resonant cavity, a hollow metal chamber designed to amplify electromagnetic signals at a specific frequency, placed inside a powerful superconducting magnet. The idea is this: if axions are passing through the detector, and if they are dark matter, they should be constantly in vast numbers. Then some small fraction of them will convert into photons inside the magnetic field. Those photons will have a frequency determined by the axion's mass. And if the cavity is tuned to that frequency, the signal will be amplified, made just barely detectable above the noise. The ADMX experiment, based in the United States, has been doing exactly this for years, scanning slowly through possible axion masses, frequency by frequency, listening for a whisper of converted light that would confirm the existence of a particle proposed for entirely different reasons half a century ago. It is painstaking work. The range of possible axion masses is wide, and the cavity must be tuned carefully across that range, one narrow band at a time. Each frequency requires its own period of data collection, its own careful analysis. The search moves slowly, by necessity, not because the experimenters lack urgency, but because the physics demands patience. No confirmed signal has emerged yet, but the search continues, and the sensitivity improves with each generation of the instrument. And then there is a third candidate, quieter still in some ways, sitting at the other end of the mass spectrum from the axion: the sterile neutrino. Ordinary neutrinos are already among the most elusive particles we know. They interact only through the weak nuclear force and gravity. They pass through the Earth as though it were not there. Trillions of them, from the Sun, move through every square centimeter of your body every second, and not one of them leaves a mark. The sterile neutrino would be a heavier cousin of these already ghostly particles, but with one crucial difference: it would not interact through the weak force at all, only gravity, making it even more invisible than the ordinary neutrino, which is already nearly invisible. If sterile neutrinos exist and have the right mass, they could have been produced in the early universe in sufficient quantities to account for the dark matter we infer today. They would cluster gravitationally. They would form halos around galaxies. They would behave in all the ways we can measure gravitationally, exactly as dark matter behaves. But sterile neutrinos, unlike axions, offer a different kind of window. A sterile neutrino is not perfectly stable. Over vast stretches of time, it can decay. And when it does, it produces two things: an ordinary neutrino, which escapes undetected, and a single X-ray photon. That photon carries away exactly half the sterile neutrino's rest mass energy, which means that if sterile neutrinos all have the same mass, their decay photons will all have the same energy. A single, sharp spectral line, sitting at a fixed position in the X-ray spectrum, faint, but in principle distinguishable from the broader, more diffuse X-ray emission produced by hot gas in galaxy clusters. This is a different kind of search, not a particle detector buried underground, not a resonant cavity inside a magnet, but a telescope, pointed at places where dark matter should be densest, looking for a line that should not be there if only ordinary matter were present. And something has been seen. In 2014, astronomers analyzing X-ray observations of galaxy clusters reported a faint, unexpected line at an energy of approximately 3.5 kiloelectronvolts. It appeared in data from several different clusters observed by more than one telescope at a position in the spectrum that did not correspond to any known emission line from ordinary atomic physics. The signal was tentative, the statistical significance modest, and the interpretation immediately contested. Some analyses found it, others, looking at different data sets or different regions of sky, did not. The debate has continued in the years since, with new observations adding complexity rather than resolution. It may be a sterile neutrino decay line. It may be an unresolved contribution from some ordinary astrophysical process not yet fully accounted for. It may be an instrumental artifact. The data, as of now, do not compel a conclusion. But the fact that such a search is possible at all is itself worth sitting with for a moment. The idea that a particle interacting only through gravity, a particle so weakly coupled to the rest of physics that it leaves almost no trace, might nonetheless announce itself through a single, quiet line of X-ray light, is a remarkable thing. It means the universe, even in its most hidden aspects, is not entirely silent. It means there are frequencies and wavelengths and energies where the invisible might just barely speak. We have not yet heard it clearly, but we are listening, with instruments of extraordinary delicacy, pointed at the densest concentrations of invisible mass we know, waiting for a line in the spectrum that would change everything we thought we understood about what the universe is made of. Quietly, patiently, the way all the best listening is done. There is another candidate worth resting with for a moment, one that does not require any new particle at all: primordial black holes. These are not the black holes formed when massive stars collapse at the end of their lives. Those came much later. Primordial black holes, if they exist, formed in the very early universe, in the first fractions of a second after the Big Bang, when the cosmos was so dense and so hot that regions of space could collapse directly into black holes before a single atom had ever assembled itself, before any star had ignited, before any galaxy had begun to take shape. The idea is quiet in its elegance. Perhaps dark matter is not a new kind of particle at all. Perhaps it is simply mass, ordinary gravitational mass, locked away in objects too small and too dark to see, scattered through the halos of galaxies like invisible stones drifting through an invisible sea. For a time, this was considered a serious possibility. And then, in 2015, something changed. Two black holes, each roughly 30 times the mass of the Sun, spiraled into each other somewhere in the distant universe and merged. The collision sent ripples through the fabric of space-time itself, ripples that traveled for over 1 billion years before arriving at Earth as a whisper of compression and expansion, a distortion smaller than 1,000th the width of a proton. And instruments in Louisiana and Washington State, listening with extraordinary precision, heard it. That was the first gravitational wave detection, the first time humanity had ever felt the geometry of space itself move. But the detection carried information beyond the mere fact of its existence. The masses of those merging black holes, around 30 solar masses each, fell in a range that had been proposed for primordial black holes. And as more detections followed, astronomers began to ask whether the population of merging black holes seen by LIGO might be telling us something about dark matter. The answer, so far, is careful and measured. Gravitational wave observations have constrained the primordial black hole hypothesis, meaning they have ruled out certain mass ranges and certain abundances. A universe in which primordial black holes of a particular mass make up all of the dark matter would produce a merger rate inconsistent with what LIGO observes. Some windows have been closed, but not all of them. Primordial black holes in certain mass ranges, very low masses, or masses in specific intermediate ranges, remain viable contributors. They have not been eliminated. The hypothesis lives on, narrowed but not extinguished, waiting for more data to either close the remaining windows or find something unexpected inside them. And so the search continues on multiple fronts, through gravitational waves, through X-ray spectra, and through a third approach entirely, one that reaches not outward into the sky, but downward deep into the Earth. Direct detection. The idea is straightforward in principle, even if extraordinary in practice. If dark matter particles exist and pass through ordinary matter, as they are thought to do, in vast numbers every second. Then very occasionally, one of them might strike an atomic nucleus, not electromagnetically, not through light or charge, but through the weak nuclear force or through gravity alone. A collision so gentle it would be almost imperceptible, and yet, with the right instrument, in the right conditions, perhaps just barely measurable. The challenge is not finding a sensitive enough detector. The challenge is silence. The world is extraordinarily loud. At the level of individual particles, cosmic rays rain down from space continuously. Radioactive decay occurs in every material, in every wall, in the air itself. Natural uranium and thorium and rock emit particles constantly. Even the human body is mildly radioactive. In this environment, a genuine dark matter signal, perhaps one event per ton of detector material per year, or even rarer, would be buried beneath an avalanche of ordinary noise. To hear something that quiet, you have to go somewhere very quiet indeed. You go underground. The Lux Zeppelin detector sits nearly 1.5 miles beneath the surface of the Black Hills of South Dakota, inside a former gold mine. It is one of the most sensitive dark matter detectors ever built. At its heart are 10 tons of liquid xenon, cooled to temperatures near absolute zero, near the coldest temperature the laws of physics permit. Xenon is chosen because its heavy nuclei make a relatively favorable target for the kind of collision dark matter might produce, and because it can be purified to extraordinary levels, removing almost all radioactive contamination from the liquid itself. When a particle strikes a xenon nucleus, it produces two signals, a flash of light and a pulse of ionized electrons drifting upward through the liquid toward a layer of gas above. The ratio of those two signals tells physicists something about what kind of particle caused the interaction, whether it was an electron recoil from ordinary background radiation or a nuclear recoil of the kind a dark matter particle would more likely produce. The detector is surrounded by a tank of ultra-pure water, which absorbs stray radiation from the surrounding rock. And above it all, nearly 1.5 miles of earth and stone filters out the cosmic ray muons that would otherwise trigger false signals thousands of times more often than any dark matter interaction could. The rock itself is the shield. This is why underground laboratories exist at all. The Gran Sasso Laboratory in central Italy is perhaps the most storied of them. It was carved directly into the heart of a mountain in the Apennines, not built on the surface and covered, but excavated from within, so that roughly 1.5 miles of solid rock sits above the experimental halls in every direction. The mountain does not merely shelter the experiments from above, it surrounds them, muffles them, reduces the cosmic ray flux by a factor of roughly 1,000,000 compared to the surface. Inside Gran Sasso, multiple experiments run simultaneously. Dark matter searches, neutrino experiments, studies of rare nuclear decays, all sharing the same deep quiet that the mountain provides. It is a place where physicists have learned to listen for signals so faint that the ordinary world would drown them out entirely. A place where the noise of the cosmos is reduced, layer by layer, until what remains is as close to silence as human engineering has yet achieved. And in that silence, they wait. No confirmed detection has come. Not from Lux Zeppelin, not from its predecessors, not from any direct detection experiment in the decades this search has been underway. The xenon remains still. The nuclear recoils that would announce a dark matter particle have not appeared above the background. Or, if they have not yet risen clearly enough above it to be certain. This is not failure. Exactly. Each null result is itself a measurement. Each year of running without a signal tells physicists something real, that dark matter, if it interacts with ordinary matter at all, does so more rarely than a given sensitivity level could detect. The parameter space narrows. The allowed region of mass and interaction strength shrinks. The search becomes more precise with every passing year, even when nothing is found. There is something almost meditative about it. Instruments of extraordinary delicacy, resting in the deep earth, cooled to temperatures near absolute zero, listening for a single knock on a xenon nucleus that might never come, or might come tomorrow, or might have already come and been mistaken for something else. The universe does not announce its secrets on a schedule. It keeps them quietly for as long as it needs to. And the detectors wait. And so, the generations pass. Xenon 1T came first among this lineage of liquid xenon detectors, a vessel of extraordinary purity, buried deep, listening with a sensitivity that would have seemed unreachable just a decade before it was built. It heard nothing confirmed, but in hearing nothing, it drew a line, a boundary in the space of possibilities, saying, if dark matter particles exist with these masses and these interaction strengths, they are not here, not at this level of sensitivity. Then came Pandex, built beneath a mountain in southwestern China. More xenon, more shielding, more years of patient running. The same silence, but a more informative silence. The boundary moved again. The allowed region shrank further. And now, Lux Zeppelin waits in its cavern beneath the Black Hills of South Dakota, 10 tons of liquid xenon, the largest such instrument yet built, its sensitivity surpassing its predecessors by a considerable margin. It is not the last of its kind, but it is the most capable instrument of this type that has yet listened to the dark. Each of these experiments represents not just an engineering achievement, but a kind of philosophical commitment, a willingness to spend years, sometimes decades, in pursuit of something that may interact so rarely with ordinary matter that no instrument yet built could ever catch it. The physicists who design these detectors know this. They build them anyway, because the alternative, not looking, tells you nothing at all. And still, no confirmed detection. This is worth sitting with for a moment. Decades of searching, multiple generations of experiments, detectors growing larger and more sensitive with each iteration, underground laboratories on multiple continents, each one a monument to human patience. And across all of it, no dark matter particle has announced itself clearly enough to be certain. This does not mean dark matter does not exist. The gravitational evidence for it is overwhelming and comes from too many independent directions to dismiss: galaxy rotation curves, gravitational lensing, the acoustic patterns in the cosmic microwave background, the structure of the cosmic web itself. All of these point to the same conclusion. There is far more mass in the universe than we can see. But what that mass is made of, what particle, if any, carries it, remains genuinely unknown. It is possible that dark matter interacts with ordinary matter only through gravity. In that case, no direct detection experiment of the kind described here would ever find it. The xenon would remain forever undisturbed by dark matter's passage. The search would need to take a different form entirely. And so it does. There is another way to look. Rather than waiting for dark matter to knock against a nucleus in a detector, some experiments search for what dark matter might leave behind as it moves through the universe. If dark matter particles can annihilate one another when they meet, two particles colliding and converting their mass into energy, that energy must go somewhere. It must emerge as other particles, as gamma rays, or positrons, or neutrinos. Particles that travel outward from wherever the annihilation occurred and can, in principle, be detected. This is indirect detection. And the sky, it turns out, is full of places where dark matter might be dense enough for annihilations to occur at a measurable rate. The center of the Milky Way is one such place. Dark matter halos. According to simulations, tend to grow denser toward their centers. The galactic center, already a crowded and energetic region, should also be a place where dark matter particles are packed more tightly than anywhere else in the galaxy. If they annihilate, the products of those annihilations should be detectable above the background. The Fermi Gamma Ray Space Telescope was launched in 2008 and has been mapping the gamma-ray sky ever since. It watches the galactic center. It watches the dwarf spheroidal galaxies that orbit the Milky Way. Those small, dark matter-dominated systems where the ratio of invisible to visible mass is among the highest known anywhere. If dark matter annihilates, these are among the most promising places to look. And Fermi has found something. There is an excess of gamma rays coming from the direction of the galactic center, a glow of high-energy light that is somewhat brighter than the known sources of gamma radiation in that region would predict. It has been studied carefully for years. Its spectrum and spatial distribution are, in some respects, consistent with what dark matter annihilation might produce. But the galactic center is not a quiet place. It is crowded with pulsars, rapidly spinning neutron stars that emit gamma rays, and with other energetic phenomena that are difficult to model precisely. A large population of unresolved pulsars, too faint to be detected individually but collectively bright, could produce a gamma-ray excess that looks, in aggregate, very much like what dark matter annihilation would produce. The two explanations have not been cleanly separated. The excess is real. Its origin is not yet known. This is the nature of indirect detection. The signals, if they exist, are subtle. They sit atop backgrounds that are themselves complex and not perfectly understood. Distinguishing a dark matter signal from astrophysical mimics requires not just sensitivity, but a deep understanding of everything else that produces gamma rays in the same region of sky. That understanding is still being built. The dwarf galaxies offer a somewhat cleaner environment. They are quieter, fewer pulsars, less ongoing star formation, less of the energetic activity that complicates the galactic center. Fermi has searched them carefully and found no significant excess. This non-detection places constraints on how strongly dark matter can annihilate, constraints that are beginning to press against the parameter space where WIMPs were once expected to live. Meanwhile, above the atmosphere, another instrument watches from a different vantage point. The Alpha Magnetic Spectrometer, AMS-02, has been mounted on the International Space Station since 2011. It is a particle physics detector in orbit, measuring the composition of cosmic rays that stream through the solar system from all directions. Among the particles it counts are positrons, the antimatter counterparts of electrons. Positrons are produced by various astrophysical processes. But if dark matter particles annihilate in the galaxy, positrons are among the particles that would be released. A dark matter signal might appear as an excess of positrons above what ordinary astrophysical sources would predict, particularly at certain energies. AMS-02 has measured a positron excess. The fraction of positrons among cosmic ray electrons and positrons rises at energies above roughly 10 billion electron volts, more than simple models of cosmic ray propagation would suggest. This excess was first hinted at by earlier experiments and has been confirmed with greater precision by AMS-02. But here, again, the interpretation is uncertain. Pulsars are efficient producers of positrons. A nearby pulsar, or a population of them, could account for the observed excess without any dark matter at all. The signal is real. Its source remains open. There is a pattern here, if you are listening for it. Every indirect detection search finds something interesting, and every interesting thing turns out to have at least one conventional explanation that cannot yet be ruled out. The universe is full of energetic processes that produce the same particles dark matter annihilation would produce. Separating the dark matter signal from the astrophysical noise requires a precision that current instruments approach but have not yet achieved. And so the search continues on multiple fronts simultaneously. Underground, in the xenon, above the atmosphere, in the cosmic rays, across the gamma-ray sky, in the glow of dwarf galaxies, and the complicated brightness of the galactic center. Each instrument asking the same question in a different language. Each waiting, in its own way, for an answer that has not yet come. There is one more place to look. Not underground, and not above the atmosphere, but inside the most energetic collisions human beings have ever deliberately created. At the Large Hadron Collider, buried beneath the French and Swiss countryside, protons are accelerated to within a fraction of a percent of the speed of light, and then aimed at each other. The collisions happen billions of times per second, each one a brief, violent recreation of conditions that last existed in the very early universe. And in the wreckage of each collision, physicists look for something that should not be missing. The logic is quiet but precise. When two protons collide, the total momentum of the system is known. Everything that emerges from the collision, every particle, every fragment, should balance that momentum exactly. If the numbers do not add up, if there is a gap, an absence, a direction in which momentum seems to have vanished, then something left the detector without being seen. That something could be a dark matter particle. A particle that passed through the entire detector, through layers of silicon and crystal and steel, without leaving a single trace. The way dark matter passes through everything, always, without stopping. This signature is called missing transverse energy, and it is, in a sense, the shape of an absence. Physicists do not see the particle itself. They see the hole it left behind in the accounting. The Large Hadron Collider has now completed 3 major operational runs. Each run pushed deeper into the energy landscape, probing mass ranges and interaction strengths that had never been tested before. And across all of that data, across all of those billions upon billions of collisions, no confirmed dark matter signal has emerged. This does not mean dark matter does not exist. It means that if dark matter particles can be produced in proton collisions, they are either too heavy for the current energy range, or they interact too weakly to be produced at a meaningful rate, or they couple to ordinary matter in ways that do not leave the expected signatures. The absence is informative. It narrows the space of possibilities. It tells theorists which corners of their models are becoming difficult to defend. And the collider will run again, at higher energies with more sensitive detectors. The search there is not finished. It has simply not yet found what it is looking for. There are those who have looked at all of this evidence, the rotation curves, the lensing, the structure formation, the CMB, and asked a different kind of question. What if the problem is not missing matter? What if the problem is our understanding of gravity itself? This is not a fringe idea. It was developed carefully, mathematically, by a physicist named Mordechai Milgram in the early 1980s. His proposal is called Modified Newtonian Dynamics, MOND. The core of the idea is this. Newton's law of gravity works extraordinarily well in the regimes we have tested it, in the solar system, in dense environments, wherever accelerations are strong. But what if, at very low accelerations, the kind experienced by stars at the outer edges of galaxies, gravity behaves slightly differently than the standard formula predicts? What if it falls off more slowly? If that were true, you would not need invisible matter to explain why outer stars orbit too fast. The modified gravity would hold them in place on its own. And for individual spiral galaxies, MOND works. It works surprisingly well. Given only the distribution of visible matter in a galaxy, MOND can predict the rotation curve with a precision that is In many cases, genuinely striking. There is a relationship between the distribution of ordinary matter and the shape of the rotation curve that mode captures naturally, and that dark matter models have to work harder to explain. This is worth sitting with quietly. The fact that the visible matter alone seems to know something about the rotation curve, that the two are correlated in a way that feels almost too clean, is one of the more thought-provoking patterns in this entire field. And yet, MOND encounters serious difficulties when it moves beyond individual galaxies. Galaxy clusters are one problem. The same modification that works so well for spiral galaxies does not fully account for the dynamics of clusters. Even with modified gravity, clusters appear to contain more mass than their visible matter provides. MOND advocates sometimes propose that ordinary neutrinos, which have a small but non-zero mass, could make up some of this deficit, but the numbers are difficult to reconcile completely. The cosmic microwave background is another problem. The precise ratios of the acoustic peaks in the CMB, those subtle temperature fluctuations imprinted on the sky from 380,000 years after the Big Bang, are naturally explained by a universe containing a specific density of dark matter. Reproducing those ratios with modified gravity alone requires additional assumptions that become increasingly elaborate. And then there is the bullet cluster. Two galaxy clusters that collided. The hot gas, which makes up most of the ordinary matter in each cluster, was slowed by pressure as the clusters passed through each other. It lagged behind. It piled up in the middle. But the gravitational mass, mapped through lensing, did not lag. It continued forward, as if it had passed through the collision without noticing. This spatial separation, mass here, gas there, is very difficult to explain if gravity simply follows the matter. In MOND, gravity is tied to the distribution of ordinary matter. If the gas slowed down, the gravitational influence should have slowed with it, but it did not. The lensing maps show mass where there is very little ordinary matter to source it. To explain the bullet cluster within a MOND framework requires invoking some form of unseen mass anyway, which begins to resemble, in some ways, the hypothesis it was meant to replace. This does not make MOND wrong in every context. It may be capturing something real about the relationship between ordinary matter and gravitational dynamics at low accelerations. Some researchers are working on relativistic extensions of MOND, more complete theories that might address the cluster and CMB problems while preserving what works at the galaxy scale. The work is ongoing, and it is serious work. But as a complete replacement for dark matter, MOND has not yet succeeded. The evidence that something beyond ordinary matter and ordinary gravity is present, especially in clusters, especially in the CMB, especially in the bullet cluster, remains, for now, more naturally accommodated by dark matter than by any modification of gravity that has been fully developed. And so, the picture holds its shape. Something is there. Something that does not shine, does not scatter light, does not slow down when it passes through a cloud of hot gas. Something that was present early enough to seed the first structures and massive enough to hold galaxies and clusters in configurations they could not maintain on their own. Whether it is a WIMP or an axion or a sterile neutrino or something no one has yet written down. Whether it is one particle or a family of particles or something stranger still, the gravitational evidence for its presence is woven through the universe at every scale we can measure. The detectors wait in their quiet underground chambers. The telescopes trace the slow distortions of distant light. The collider sends its protons into each other, again and again, looking for the shape of something missing. And the universe holds its answer gently, the way it always has, present in everything, visible in nothing, patient beyond any measure of time we carry with us into sleep. There are other ways to think about what dark matter might be. Not every candidate moves slowly through the universe the way WIMPs are expected to. Some hypothetical particles would have been born with considerably more thermal energy, moving faster, spreading more widely in the early universe before gravity could gather them into tight concentrations. These are called warm, dark matter candidates, and their higher velocities would leave a mark on the universe that cold, dark matter would not. When particles move quickly, they stream out of small gravitational wells before those wells can deepen into structures. They smooth things over. They erase the smallest clumps before those clumps have a chance to become anything. This means a universe filled with warm, dark matter would contain fewer small galaxies, fewer small halos, fewer of the tiniest structures that cold, dark matter simulations tend to produce in abundance. In some ways, that is appealing. Cold, dark matter simulations have long predicted more small satellite galaxies around the Milky Way than astronomers actually observe. Warm, dark matter offers one possible explanation for that quieter, less crowded picture. But the universe keeps its own records. Dwarf galaxies, small, faint, gravitationally bound collections of stars, exist in numbers that constrain how warm any dark matter candidate can be. If the particles moved too quickly in the early universe, too much small-scale structure would have been erased, and the dwarf galaxies we do observe could not have formed. There is also a record written in the light of distant quasars. Between us and those ancient, luminous objects lies a vast web of hydrogen gas. As the quasar's light travels toward us, it passes through clouds of that gas, and each cloud absorbs a slightly different wavelength. The result is a pattern of absorption lines in the spectrum, a kind of fossil record of how matter was distributed across enormous distances and deep into the past. This is called the Lyman alpha forest, and it is sensitive to the smallest scales of structure in the universe. Warm, dark matter, by smoothing out those small scales, would leave a quieter, less textured pattern in the forest. The observed pattern is not that quiet. It carries detail at small scales that places firm limits on how fast any warm, dark matter particle could have been moving when the universe was young. So the warmth of the candidate is bounded from both sides. Too cold, and certain small-scale puzzles remain. Too warm, and the structures we actually see could not exist. The answer, if there is one, lives somewhere in that narrow space. And yet, temperature is not the only dimension along which dark matter models can vary. There is another possibility, quieter in its assumptions, but rich in its consequences. What if dark matter particles do not simply pass through each other the way cold dark matter is usually assumed to do? What if they scatter? What if, when two dark matter particles come close enough, something happens between them, not through electromagnetism, not through the strong force, but through some interaction entirely their own? This is the idea behind self-interacting dark matter. In the standard picture, dark matter particles move through each other like ghosts, feeling only the collective pull of gravity. But self-interacting dark matter would behave more like a gas in some respects, particles exchanging momentum when they meet, redistributing energy through a halo over time. The consequences would be subtle, but measurable. In the centers of galaxies, where dark matter is densest, and collisions would be most frequent, self-interactions would tend to smooth out the distribution. They would transport energy from the hotter outer regions inward, or from the denser center outward, depending on the regime. Over time, this would soften what would otherwise be a sharp, steep concentration of mass at the core. Astronomers describe this in terms of density profiles. A cuspy profile rises steeply toward the center, like a spike. A chord profile flattens out, like a plateau. Cold, dark matter simulations tend to produce cusps, But observations of certain galaxies, particularly low-surface brightness galaxies and some dwarf galaxies, suggest cores. This tension has been present in the data for some time. Self-interacting dark matter offers a way to resolve it. The rate at which particles scatter, described by a quantity called the self-interaction cross-section, determines how efficiently the center is smoothed. A larger cross-section means more scattering, more redistribution, a softer core. A smaller cross-section leaves the profile closer to what cold, non-interacting dark matter would produce. By comparing the observed density profiles of many galaxies across a range of masses and environments, astronomers can constrain that cross-section. The data suggest, tentatively, that if self-interactions exist, they are modest but not negligible. Perhaps a few interactions per particle per billion years, enough to matter at the centers of galaxies, not enough to disrupt the large-scale structure that cold dark matter explains so well. It is a delicate balance, and the measurements are still accumulating. But there is one more direction in which the imagination of theorists has reached, and this one is perhaps the strangest of all. It begins with quantum mechanics. Every particle in the quantum description of nature also has a wave character. The smaller the particle's mass, the longer its associated wavelength, the de Broglie wavelength, named for the physicist who first described this relationship. For ordinary particles, this wavelength is so small, it has no practical consequence at the scales of galaxies or even atoms. But for a particle of extraordinarily small mass, the wavelength could become very large indeed. Fuzzy dark matter takes this idea seriously. It proposes that dark matter consists of ultralight particles, axion-like in character, but with masses so small they are almost beyond imagining. Perhaps 100 millionth of a billionth, the mass of an electron. At such masses, the quantum wave nature of the particle would not be confined to subatomic scales. It would extend across enormous distances. The de Broglie wavelength of a fuzzy dark matter particle could be as large as a kiloparsec, roughly 3,000 light-years, a distance comparable to the size of a small galaxy. This means the particle would not behave like a point moving through space. It would behave like a wave spread across a region the size of a small galaxy. And where waves exist, interference exists. Regions where the wave reinforces itself, and regions where it cancels. On the smallest scales, this quantum fuzziness would smooth out structure the way warm dark matter does, but through an entirely different mechanism, not thermal velocity, but the fundamental uncertainty written into the particle's nature. The centers of galaxies, in this picture, would not be cusps or even simple cores. They would be quantum solitons, stable, smooth concentrations of wave-like dark matter held in shape by the balance between gravity pulling inward and quantum pressure pushing outward. Surrounding each soliton, the halo would have a granular texture, a constantly shifting pattern of constructive and destructive interference, like the surface of very still water disturbed by many overlapping ripples. It is a picture that is difficult to hold in the mind, and it may not be correct. The constraints from the Lyman alpha forest and from the observed properties of dwarf galaxies press on fuzzy dark matter as well, limiting how light the particle can be. But it remains a genuine possibility. A universe in which the invisible architecture holding everything together is not made of slow-moving particles or fast-moving particles, but of something more like a vast, coherent quantum field spread across galactic distances, shaping structure through the mathematics of waves rather than the mechanics of collisions. The universe does not seem to mind how strange its answers are. It simply holds them quietly at every scale. And yet, for all the strangeness of waves and solitons, and quantum fields stretched across galactic distances. There is something else about dark matter that is easy to overlook. Something quieter, and in its own way, just as profound. Dark matter does not cool. That single fact shapes almost everything about the way it exists in the universe. When ordinary matter falls together under gravity, it does something that seems almost instinctive. It radiates. Atoms collide, heat up, and shed that energy as light. Gas clouds glow. Dust grains emit faint infrared warmth. Stars burn. Even the diffuse gas between galaxies slowly loses energy to radiation, settling, compressing, finding lower and lower states. This is how ordinary matter makes things. It cools, and in cooling, it falls inward. It loses energy, and in losing energy, it collapses. Disks form because rotating gas can radiate away the energy of its random motions while conserving angular momentum, flattening into a plane. Planets form because cooling gas and dust can clump and stick. Stars form because collapsing clouds can shed enough heat to let gravity win. Dark matter cannot do any of this. It has no way to shed energy. It does not emit light. It does not radiate at any wavelength. When dark matter particles move through space, they carry their energy with them, and they keep it. There is no release, no settling, no slow surrender to a lower state. And so, dark matter halos remain what they have always been: large, diffuse, roughly spherical, slowly rotating structures that never quite collapse into anything denser. They are not disks. They are not compact. They are vast, gentle clouds of invisible mass, held in a kind of permanent suspension between gravity pulling inward and the kinetic energy of their own motion pushing back. The halo surrounding the Milky Way is one of these structures. It extends far beyond anything you could see if you looked up at the sky on the clearest night. The visible disk of our galaxy, the stars, the spiral arms, the glowing band of the Milky Way is only a small, bright region near the center of something much larger. The dark matter halo reaches outward for hundreds of thousands of light years in every direction. A sphere of invisible material so large that the entire visible galaxy sits inside it like a lantern inside a room. And that halo is not light. Estimates place its total mass at roughly 1 trillion times the mass of the Sun. 1 trillion solar masses of material that emits nothing, reflects nothing, and can only be known through the gentle pull it exerts on everything around it. The stars of the Milky Way orbit within it. The satellite galaxies of the Milky Way are embedded in it. Even the local group, the small family of galaxies to which the Milky Way belongs, is shaped in part by the dark matter halos of its members. All of that, and none of it visible. There is something worth sitting with in that thought. The galaxy you live in is mostly something you cannot see. The part that glows, the part that makes the night sky. What it is a small fraction of the whole. The rest is this quiet, diffuse, ancient halo, holding everything in place without announcing itself at all. And here is where the scale becomes personal, in a way that is almost difficult to accept. If WIMPs are real, if the dark matter halo of the Milky Way is made of weakly interacting massive particles, then those particles are not only out there, somewhere far away. They are here. They are passing through this room, through the walls, through the floor, through you, right now, as you lie still. Roughly 100,000 of them, every second, through a space no larger than your open hand. Not because they are seeking anything, not because they are drawn to you in particular, simply because the halo is everywhere, and you are inside it, and the particles move through ordinary matter the way light moves through glass, not stopped, barely slowed, almost entirely unaffected by the encounter. You would not feel them. There is no sensation, no warmth, no signal of any kind. The interaction, if it happens at all, is so rare and so faint that the most sensitive detectors ever built, buried deep underground, cooled to temperatures near absolute zero, have not yet caught a single confirmed event. But the particles, if they exist, are there. The local density of dark matter near Earth, the concentration of it in this small region of the halo, is estimated at somewhere between 0.3 and 0.4 GeV per cubic centimeter. That is a unit from particle physics, a measure of energy and mass at the scale of atomic nuclei. It is a small number in absolute terms. The dark matter near you is not dense by any ordinary measure, but it is present, continuously in every cubic centimeter of the space around you. A faint, invisible medium, everywhere at once, passing through everything without leaving a mark. Some experiments have tried to catch not a single collision, but a pattern. The idea is subtle. As Earth moves around the Sun, it moves through the dark matter halo at slightly different angles and speeds at different times of year. In June, Earth's orbital velocity adds to the Sun's motion through the halo. In December, it partially subtracts. This means that if dark matter particles are colliding with atomic nuclei in a detector, the rate of those collisions should rise and fall with the seasons, a gentle annual rhythm, like a tide. The Gamma Libra experiment, running deep beneath the Gran Sasso mountain in Italy, has been measuring exactly this kind of modulation for decades, and it reports a signal, a seasonal variation in its detector, rising and falling with a period of 1 year, with a phase consistent with what dark matter would produce. The signal is statistically significant. It has persisted across multiple phases of the experiment, over many years of data, and yet, other experiments using different detector materials and different methods have not seen it. Lux Zeppelin, Xenon, Pandax, detectors with greater sensitivity to many dark matter models, have found nothing. The tension between Gamma Libra's signal and the null results of other experiments has not been resolved. It remains one of the quieter, more persistent puzzles in the field. The modulation could be dark matter. It could also be something else. Some seasonal variation in background radiation, some effect of temperature or humidity deep inside the mountain, some systematic influence that mimics the expected signal without being the thing itself. The debate continues, carefully, in the language of statistics and systematic uncertainties. This is how science often looks from the inside. Not a clean moment of discovery, but a long, patient argument between data sets. A signal that might be real and might not be, held in suspension, while more evidence accumulates. The universe does not always make itself easy to read. And dark matter, more than almost anything else in physics, seems to resist being read at all. It shapes the galaxy you live in. It passes through your body in vast numbers every second. If the leading theories are correct, it has been present since before the first stars formed, guiding the growth of every structure in the cosmos. And still, it has not been caught. Not directly. Not yet. The halo remains what it has always been: vast, diffuse, patient, and quiet, holding the visible universe in place from the outside, present everywhere, known nowhere. And yet the motion continues. Earth does not sit still inside the dark matter halo. It moves. The entire solar system moves, carried along by the Milky Way's slow rotation, drifting through the surrounding cloud of invisible particles at roughly 220 kilometers every second. And as Earth traces its own orbit around the Sun, that velocity shifts slightly. In June, Earth moves in roughly the same direction as the solar system's broader motion through the halo. The two velocities add together. In December, Earth moves in the opposite direction, and the combined speed is a little lower. The difference is small, perhaps a few percent, but it is enough, in principle, to leave a mark on a detector. A gentle annual rhythm, rising and falling with the seasons, not because of anything the sun does to dark matter, but simply because of geometry, because of the angle of motion through an invisible sea. This is what the Gamma experiment claimed to see, a signal that breathes with the calendar. And the claim has never quite gone away, even as other experiments have searched the same parameter space and found nothing. The tension remains, unresolved, carefully documented, and quietly troubling to everyone involved. Other experiments have tried to replicate the search, some with different target materials, some with different shielding, some in different locations beneath different mountains. The results have not converged. And so the annual modulation sits in the literature like an open question that no one has yet been able to close. What comes next is not a single experiment, but a generation of them. The detectors being built now are larger than anything that came before. Darwin, the dark matter WIMP search with liquid xenon, is designed to hold around 50 tons of liquid xenon, 5 times more than the current leading instruments, Pandex XT. The next phase of the Chinese experiment aims for a similar scale. These are not incremental upgrades. They represent a qualitative shift in sensitivity, the kind that takes years of engineering and careful design to achieve. But there is a horizon ahead of them, a natural boundary that no xenon detector, however large, can easily cross. It is called the neutrino floor. Ordinary neutrinos, the ghostly particles produced in vast numbers by the sun, pass through matter almost as freely as dark matter does. They interact so rarely that most of them travel through the entire Earth without touching a single atom. But not all of them. In a detector large enough and sensitive enough, solar neutrinos will occasionally collide with a xenon nucleus, and that collision will look, to the detector, almost exactly like what a dark matter particle would look like. The neutrino floor is not a wall. It is more like a fog, a background that grows thicker as detectors grow more sensitive, until the signal you are searching for becomes difficult to distinguish from the noise of particles you were never trying to detect. At that depth of sensitivity, the sun itself becomes a source of interference. The same star that makes life possible on this planet begins to obscure the search for what holds the galaxy together. There are ways to work around it. Directional detectors that could track which way a recoiling nucleus moves might distinguish solar neutrinos, which arrive from one direction, from dark matter particles, which should arrive from all directions at once. But directional detection at scale is technically demanding in ways that have not yet been fully solved. The next generation will approach the floor. What lies beyond it is still being designed. And so, the search continues its patient descent. Deeper underground, colder, quieter, larger, more precise. Each generation of experiments reaching further into the silence, listening for something that has never made a sound. While the detectors wait in their caverns, the universe above them carries on doing what it has always done. Dark matter's influence on the cosmos did not begin recently. It began early, earlier than the first stars, earlier than the first galaxies, earlier than almost anything we would recognize as structure. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen for the first time. Before that moment, ordinary matter was locked in a hot, dense plasma, constantly scattering photons, unable to move freely under gravity's pull. Dark matter was not bound by that constraint. It had been clustering quietly for hundreds of thousands of years already, building the faint overdensities that would eventually become the scaffolding of the cosmos. When ordinary matter was finally released from the plasma, when the universe became transparent and light streamed freely for the first time, it did not fall into an empty, uniform space. It fell into a landscape that dark matter had already shaped. The gravitational wells were already there, waiting. Ordinary matter simply followed. This is why the large-scale structure of the universe looks the way it does. The great filaments of galaxies stretching across hundreds of millions of light years. The vast, empty voids between them. The clusters where thousands of galaxies gather in slow gravitational embrace. None of it would have formed in time or in the right proportions without the invisible architecture that preceded it. Computer simulations that include dark matter reproduce the observed universe with quiet accuracy. Simulations that leave it out produce something unrecognizable. The visible universe is, in a sense, a secondary structure, built inside a framework it cannot see. Every galaxy you have ever seen in an image, every spiral arm, every elliptical cloud of ancient stars, every irregular smear of light at the edge of the observable cosmos sits inside a dark matter halo that outweighs it many times over. The halo came first. The stars came after, drawn in by gravity, settling into the shapes we now observe. The light is the consequence. The darkness was the cause. And whatever dark matter turns out to be, whether it is a WIMP that has simply evaded every detector so far, or an axion oscillating in the background of every magnetic field in the universe, or something that has not yet been named or imagined, its role in the history of the cosmos is not in doubt. The evidence for its gravitational influence is written in too many places at once, in the rotation of galaxies, in the bending of light around clusters, in the acoustic patterns frozen into the oldest light in the universe, in the distribution of matter across scales so large that the mind can only approach them slowly, in the quiet. It is not a gap in our knowledge so much as a shape in it, a presence defined entirely by what it does rather than what it is. Something that has been here since nearly the beginning, working in silence, building the conditions for everything that followed. The stars formed because of it. The galaxies held together because of it. The filaments stretched across the cosmos because of it. And somewhere in that long chain of consequence, a small rocky planet formed around an ordinary star, and on that planet, creatures eventually arose who looked up at the night sky and began to wonder what was holding it all together. They are still wondering. The detectors sit in their mountains and their salt mines, cooled to temperatures that approach the stillness of deep space, waiting for a single nucleus to tremble. The telescopes map the subtle distortions in the shapes of distant galaxies, tracing the invisible mass between here and there. The theorists write equations that describe particles no one has ever seen. And the halo continues. Vast, diffuse, patient, older than the sun, older than the earth. Present in the space around you right now, passing through the walls, through the floor, through the quiet weight of your body as you rest. A quiet architecture, holding everything in place. And still the question remains, not just what dark matter is, but why the universe arranged itself this way at all. Why this particular balance? Why 5% visible, 27% dark matter, 68% something else entirely? Why these numbers and not others? There is no answer to that yet. Only the numbers themselves, sitting quietly in the data. But there is another question that lives alongside it, one that reaches even further back, to the very first moments after the beginning. When the universe was new, not millions of years old, not thousands, but fractions of a second old, it was filled with something extraordinary. equal parts matter and antimatter. For every particle that would one day become a proton, an electron, an atom, a star, there was a corresponding antiparticle, a mirror image, identical in mass, opposite in charge. And when matter meets antimatter, they do not simply collide, they annihilate. They vanish into pure energy, into light, into nothing that can build a galaxy or a hand or a thought. If the early universe had been perfectly symmetric, if matter and antimatter had existed in exactly equal measure, they would have destroyed each other completely. Every particle erased by its counterpart, every antiparticle erased in return. And what would have remained is a universe of light and nothing else. No atoms, no dust, no planets, no one to notice the silence. And yet, here you are. Something survived. Not much, by the standards of what was lost. For roughly every billion antimatter particles, there were roughly 1,000,000,001 matter particles. A difference so small, it is almost nothing. Almost. But almost is everything. That single extra particle in every billion, that tiny, quiet asymmetry, is the reason the visible universe exists at all. Every star you have ever seen in the night sky, every mountain, every ocean, every living thing, all of it descended from that vanishingly small surplus, a remainder left over after the Great Cancellation. Physicists call this the matter-antimatter asymmetry, and they have been trying to understand it for decades. In 1967, a physicist named Andrei Sakharov identified 3 conditions that any theory must satisfy to explain how this asymmetry could have arisen naturally. The universe must have violated the conservation of baryon number, the quantity that counts the difference between particles and antiparticles. It must have done so outside of thermal equilibrium, so the process could not simply reverse itself, and it must have treated matter and antimatter differently. That third condition has a name: CP violation. CP stands for charge parity. Charge symmetry means that swapping a particle for its antiparticle should leave the physics unchanged. Parity symmetry means that mirroring the spatial coordinates of a system should leave the physics unchanged. Together, CP symmetry would mean that matter and antimatter behave identically in every interaction. But they do not. Experiments have confirmed that certain particles, particularly those containing quarks called bottom quarks, and particles called kaons, decay in ways that are subtly different depending on whether they are matter or antimatter. The difference is small, measurable, but small. And as far as physicists can determine, it is not nearly large enough to account for the full asymmetry we observe. The known CP violation explains only a fraction of the surplus that allowed the visible universe to exist, which means something is missing. There may be additional sources of CP violation that have not yet been found, perhaps in the behavior of neutrinos, which are notoriously difficult to study, and which may themselves violate CP symmetry in ways not yet measured. The NOVA and T2K experiments have been searching for exactly this, sending beams of neutrinos and antineutrinos across hundreds of kilometers of rock, comparing their behavior, looking for the asymmetry that might help close the gap. The results so far are suggestive, hints of a difference, but not yet conclusive. And so the question remains open, quietly open. The way the deepest questions tend to be, it is worth sitting with what this means. The universe, in its first moments, was engaged in a kind of vast and violent symmetry breaking, conditions so extreme that the forces of nature behave differently than they do today, temperatures so high that the distinction between certain fundamental forces had not yet emerged, and somewhere in that chaos, in that unimaginable density of energy and particle and antiparticle, something tipped the balance, just slightly. just enough. And then the annihilation came. Particle meeting antiparticle across the entire observable universe, releasing energy, disappearing. A process that lasted only fractions of a second, but consumed nearly everything that existed. What remained was the residue, the 1 in a billion surplus. Cooling now, expanding, beginning the long, slow process of becoming something. The protons and neutrons that survived began to combine minutes after the beginning, forming the first atomic nuclei, hydrogen, helium, a trace of lithium. This is called Big Bang nucleosynthesis, and the ratios it produced match what astronomers observe in the oldest, most pristine regions of the universe. Another quiet confirmation that the model is, at least in its broad strokes, correct? Hundreds of thousands of years later, when the universe had cooled enough for electrons to settle into orbit around those nuclei, the first neutral atoms formed, and the universe became transparent. The light that had been trapped, scattering endlessly through the dense fog of charged particles, was suddenly free to travel. That light is still traveling. We detect it today as the cosmic microwave background, a faint glow in every direction, carrying the imprint of conditions from nearly 14 billion years ago. And embedded in that glow are the acoustic oscillations, the pressure waves that moved through the early universe like sound through a dense medium. Their patterns encode the density of ordinary matter, the density of dark matter, the geometry of space itself. All of it written in the temperature fluctuations of ancient light. Two mysteries, then woven together in the same ancient signal. Dark matter, shaping the gravitational landscape before ordinary matter could move freely, and the matter-antimatter asymmetry, which ensured there was any ordinary matter at all to be shaped. Without the asymmetry, there would be no atoms for dark matter to gather. Without dark matter, there would be no structure for those atoms to fall into. The two mysteries are not the same, but they are companions, each one a condition for the other to matter. And both of them remain, in their deepest form, unsolved. The detectors continue their patient work. The accelerators collide particles at energies that briefly recreate conditions from the universe's earliest moments, searching for new sources of CP violation, for particles that behave differently than their antiparticles in ways not yet cataloged. The theorists extend their equations into territory that has not yet been tested, proposing mechanisms, leptogenesis, electroweak baryogenesis, others that might account for the full asymmetry. None of it is settled. All of it is ongoing. And perhaps that is fitting, that the questions which reach furthest back to the first fractions of a second, to the conditions that made existence possible, should be the ones that resist the quickest answers. The universe does not seem to be in a hurry to explain itself. It simply continues, expanding quietly into whatever lies beyond its current edge, carrying within it the dark matter halos, the galaxies, the stars, the small warm planets, and the creatures on those planets who lie still in the dark and wonder how any of it came to be. The asymmetry that saved everything was almost nothing. And from almost nothing, all of this. And yet, the story does not end there. There is another quiet mystery woven through everything we have just described. Another layer of the universe that does not announce itself, does not glow, does not leave a trace of light at any wavelength. And yet without it, none of the rest would hold together. Everything you have ever seen, every star, every planet, every grain of dust drifting through a sunlit room, all of it accounts for only about 5% of what the universe actually contains. 5%. The rest is something else entirely. Roughly 27% of the universe's total mass and energy is dark matter, a name that says only what it is not. It is not dark in the way a shadow is dark. It is dark because it has no relationship with light at all. It does not emit light. It does not absorb light. It does not reflect it. It simply exists alongside the visible world, threading through it, shaping it, holding it, and remaining, to every instrument we have built, completely invisible. The remaining 68% is something else again, called dark energy, which is a separate mystery entirely. Tonight, we stay with the dark matter. The first hint came in 1933 from an astronomer named Fritz Zwicky. He was measuring the velocities of galaxies within a large cluster, the Coma cluster, and he found something that did not add up. The galaxies were moving far too fast. If only the visible mass were holding them together. They should have scattered long ago. Something unseen had to be providing the extra gravity. He called it missing mass. Most of his contemporaries were not ready to take the idea seriously. Decades passed. Then, in the 1970s, Vera Rubin and Kent Ford turned their instruments toward spiral galaxies and measured how fast stars orbit around the galactic center. In an ordinary gravitational system, the way planets move around the sun, objects farther from the center should orbit more slowly. The outer planets of our solar system move with a kind of patient slowness that reflects how gravity weakens with distance. But the stars at the edges of spiral galaxies did not slow down. Their orbital speeds remained flat, almost constant, far beyond the visible disk of the galaxy, as if something invisible were adding mass at every radius, keeping the gravitational pull strong, even where no stars could be seen. The only explanation that fit was a vast halo of unseen matter surrounding each galaxy, extending far beyond the light, far beyond anything a telescope could detect. The dark matter halo of our own galaxy, the Milky Way, extends roughly 100 times farther than the visible stellar disk. It contains, by current estimates, something close to 1 trillion solar masses of invisible material, 1 trillion suns worth of something we cannot see, cannot touch, cannot name with certainty. And yet, we can feel its shape. Gravitational lensing allows astronomers to map dark matter the way you might map an invisible object by watching how it bends the light passing around it. When a massive foreground object sits between Earth and a distant galaxy, the mass curves spacetime, and the background galaxy's light bends around it. Sometimes, when the alignment is nearly perfect, the background galaxy appears as a ring of light, an Einstein ring, a circle drawn in the sky by gravity alone. The amount of bending observed around galaxy clusters consistently exceeds what the visible matter could produce. The dark matter is there, in the geometry of the light itself. One of the clearest pieces of evidence came from 2 galaxy clusters caught in the act of colliding, a system known as the bullet cluster. As the clusters passed through each other, the hot gas, which makes up most of the ordinary matter, was slowed by pressure, the way 2 clouds of smoke slow each other when they meet. But the dark matter halos passed straight through, unimpeded, continuing forward as if the collision had not happened at all. X-ray observations showed the gas lagging behind. The dark matter, mapped through lensing, had moved on. This is what dark matter does. It does not interact with itself or with ordinary matter through electromagnetism or the strong nuclear force. It responds, as far as we can tell, only to gravity, and possibly to the weak nuclear force, which operates only at extraordinarily short ranges. Because it cannot radiate energy, dark matter cannot cool. It cannot collapse into disks or dense compact objects the way ordinary matter does. This is why dark matter halos remain large and diffuse and roughly spherical, vast, slow, invisible clouds that ordinary matter falls into and condenses within, forming the galaxies we see. Dark matter was there first, in the early universe, before ordinary matter could begin to clump, because ordinary matter was still coupled to radiation, still being pushed around by the pressure of light. Dark matter was already gathering under its own gravity. Those early overdensities became the seeds, the gravitational wells into which ordinary matter eventually fell. Without them, the cosmic web of filaments and voids and galaxy clusters would not have formed the way it did. The universe we see is, in a quiet sense, the shape of dark matter's early work. The cosmic microwave background carries the imprint of all this. The subtle temperature patterns across the sky encode the acoustic oscillations of the early universe, and the ratios of those oscillations precisely constrain how much dark matter was present. The Planck satellite measured those patterns with extraordinary care, and the answer it returned was consistent with everything else. Roughly 26% of the universe's total content, in the form of something that has never been directly detected. Many candidates have been proposed. The most studied is the WIMP, a weakly interacting massive particle, with a mass perhaps 10 to 1,000 times that of a proton, interacting through the weak force. The appeal of WIMPs is partly mathematical. A particle with roughly those properties, produced in the early universe, would naturally arrive at the observed dark matter density today. This coincidence is sometimes called the WIMP miracle, though it is more of a quiet suggestion than a proof. Axions are another possibility, extraordinarily light particles, perhaps a billionth of a billionth, the mass of an electron, originally proposed to solve a different problem in particle physics entirely. In the presence of a strong magnetic field, an axion might convert into a detectable photon. Experiments like ADMX use precisely this principle, tuning a microwave cavity inside a powerful magnet, listening for the faint conversion signal. Sterile neutrinos, heavier cousins of the ordinary neutrino, interacting only through gravity, have also been considered. A tentative X-ray signal at 3.5 kiloelectronvolts has been observed in several galaxy clusters, though its origin remains unresolved. Underground laboratories have been built to search for the direct collision of a dark matter particle with an atomic nucleus. The Lux Zeppelin detector in South Dakota holds 10 tons of liquid xenon, cooled to near absolute zero, buried deep enough that cosmic rays cannot reach it. The Gran Sasso laboratory in Italy sits inside a mountain, shielded by rock on every side. Decades of searching, successive generations of detectors, each more sensitive than the last. No confirmed detection. If WIMPs are real, roughly 100,000 of them may pass through a space the size of your hand every second, passing through you now as you lie still, through the walls, through the floor, through the earth itself, leaving nothing behind. The next generation of detectors will approach what physicists call the neutrino floor, the point at which ordinary solar neutrinos begin to mimic the signal of dark matter, setting a practical limit on how far certain strategies can reach. Whatever dark matter is, it has been shaping the universe since long before the first stars formed, since roughly 380,000 years after the beginning, when the light of the early universe finally decoupled from matter, and the dark matter halos were already deep and waiting. The visible cosmos, every galaxy, every cluster, every filament of light stretching across the sky, rests inside a structure it cannot see. A quiet architecture, built from something we have not yet named. The detectors wait in the dark underground. The sky turns slowly overhead, and somewhere in the space between the stars, 100,000 invisible particles pass through everything without a sound.